All right, so I think let's start. Hello, everyone. So we're going to talk about policy gradient today. So this is a follow-up lecture from the previous lecture on conservative policy iteration, right? Okay, so before we start, I want to ask it again. If it is possible, please turn on your video. It's always nice, to see you in faces, right? And yes, so policy optimization, one of the motivation for us to study policy optimization is that this is one of the most popular approach people use, right? So for these remarkable applications, they actually use some kind of policy optimization for learning, the final strategy, right? Either the strategy that beats human champion on Go or the strategy that beats, those top human players on those video games. Right. One of the reasons is that actually policy gradient is robust, right? And like the example that we have seen in the conservative policy iteration, policy gradient is robust in a sense that it gives you monotonic improvement, right? So this is always a very nice property to have, in practice. Okay, so let's recap conservative policy iteration. Right, so here is the algorithm. 3 steps in each iteration, right? So the first step is this greedy policy selection, right? So at iteration t, given the current policy pi t that we have from the previous iteration, right? Let's just find the policy that maximizes the advantage against it under its own distribution. Right? Here, recall we use regression oracle to approximately find this maximum, this argmax, right? And then the termination criteria is essentially saying that, okay, so if there's no good policy that can beat our current policy, in the sense, has larger advantage against our current policy, then we stop, right? We're at the local minimum solution or local maximum solution. And otherwise, let's just move to that greedy policy a little bit. Right? So here, alpha is often a small number. Right? So that's the algorithm. Very simple. And what guarantee we have is that the first one is about the incrementalness of the policy update. Right? So what we said is that if we do this kind of policy optimization, if we update pi t plus 1 based on this particular update procedure, then we can guarantee that the state distributions between these two, their L1 distance, in other words, their total variation distance, is bounded by alpha, this small step size, times the amplification, which is 1/1 minus gamma, right? But ignoring the amplification factor, this basically says that the two distributions are not that far away from each other if, the two policies are not that far away from each other. Right, great. And then with this property, we proved that the new policy is actually, strictly better than the previous policy if we have not terminated yet. If there exists, some non-zero, non-trivial local maximum advantage at this point. Right? So if there is advantage, our policy procedure will find a new policy that actually guarantees to be strictly better than the previous one. This is the monotonic improvement thing that we are hoping for, right? And the key message really behind this proof is that we are trading off this local maximum advantage against the distribution change, right? So if you look at the difference between the two policies, we see that this is lower bounded by this expression, where here, this term is the maximum possible local advantage that we can achieve at this moment against our current policy, right? And this is the distribution change, right? So in one hand, we want a policy we want to get the maximum local advantage. And on the other hand, we don't want too much change in the distributions. Right? So we can basically tune the parameter alpha to get the balance. So that's what we covered this Tuesday. Right? Any questions so far for the conservative policy iteration algorithm? Okay, great. So one of the motivation why we want to study policy gradient is that someone mentioned that implementing this thing, in practice might be complicated, right? It's doable, but in practice, if your policy pi is pretty huge, complicated in your network, this means that you have to keep all the policies together, right? You have to keep the history of the policies in your hand, because this guy pi t contains all the previous policies, right? And now pi t plus 1 contains all the previous policies plus this new greedy policy you computed. So you have to keep all the policy around. It's like, you're doing a sort of random forest where each policy is a decision tree in that forest, right? If you don't worry about the space, then it's okay. But this potentially going to cause a lot of computation spaces.
Wait, can you clarify that a little bit? Because I thought before we were talking about policies as basically like given a state, you get an action, right? It's basically just like a straightforward map.
Yeah.
So
okay.
Is it not straightforward to just actually combine them?
It's not, right? Like imagine imagine this is a decision tree.
Right.
Wait, how to spell decision? Okay. Decision tree. I mean, if I give you two decisions, two policies, I don't know how to combine them into one decision tree. The only way that I know is just keep them around, like you do in a random forest.
I see.
Right, or bagging, or these kind of approach.
But like, couldn't you represent like, I guess maybe if you don't have a deterministic form for it, then you can't have like ideally you'd have like a map from each state to like a probability distribution over the actions that you choose.
Yeah, you can do that if your state space is tiny. So you can enumerate all the possible states.
I see. Yeah.
But imagine your state space is huge, right? So at this stage, you'd better just keep the trees rather than maintain a table, right? Because you cannot maintain a table whose size is the number of states, right?
Okay, yeah, that makes sense.
Right. I mean, the reason we're talking about these algorithms is that we want to deal with like problems where we have infinitely many, state number of states, right? All right. Yeah. Okay, but today, we're just gonna look at a different updated procedure. We're just gonna maintain one policy, right? So we're not gonna maintain a bag of policies, a forest of decision trees. Okay, so let's just do a recap on the definitions. So we talked about two definitions of Markov decision process so far, right? So the first one is this infinite discounted setting. And the objective function is very clear. So if I give you a policy pi, then the objective function is essentially the expected total reward with proper discounting. Right? And the second definition that now we're familiar with is this finite horizon setting. Right? And the rest is the same. The objective function intuitively is still the same. It's the expected total reward across the total capital H many steps now. Right? Now, if you look at these two objective functions, right? So these objective functions, they're basically functions of the policy pi. So if I give you a policy pi, this function returns me a scalar, right? So you can really think about this as a function that takes a policy pi as input and output as scalar, right? So if we can take a gradient of this objective function with respect to a policy pi, then we can just run our favorite gradient ascent algorithm in this case, right? So that's what we're trying to do today. Right. So in order to talk about gradients, let's introduce parameterizations, right? So let's consider parameterized policy. So here I'm going to use this notation pi theta to represent this policy is parameterized by parameters theta, right? Or maybe in this way. So these two is the sort of equivalent. The left-hand side is insured of the right-hand side, right? So one example is that, maybe your state is in RD, right? So you can design maybe a 2-layer neural network. These are your parameters, theta, theta, right? And your input is state S. Your output is distribution over actions. Right? So that's one parameterization. Right? Another parameterization, maybe let's just make things even simpler. I just want to do maybe logistic regression. Right? So I have finite number of actions. Think about each action as a class. Let's just do logistic regression, right? Multi-class logistic regression. So the input is the example state. The output is distribution over classes. In this case, the distribution over actions, right? So that naturally gives us a stochastic policy. All right, so let's just rewrite the objective function. Remember, our objective function is with respect to the policies pi, right? So now the policy is uniquely parameterized by this parameter theta. So now our objective function literally is a function that maps from parameters to a value. Right, so this takes the parameter as an input, outputs a number. Right, so that means that if we can compute the gradient of this objective function with respect to our policy's parameters, then we get to this very simple, the simplest possible reinforcement learning algorithm, right? So this is a gradient ascent. Right, and then we can repeat this process until convergence, and by the probability of gradient ascent, we will guarantee that at least we converge to some local minimum solution, right? A solution where a gradient norm is 0. But the key question for today is how to compute this gradient, right? And especially, we will not be able to compute the expectation exactly, right? How we can actually approximately compute this gradient using finite number of samples. Right, so the outline for today. So to answer, the question in the previous slide, let's look into the 3 steps. So the first step is a bit of orthogonal to reinforcement learning. So let's just do a recap on gradient descent and specifically on stochastic gradient descent. All right, and then let's do a warm-up. Let's see how we can compute a gradient using this trick called importance sampling. And then let's just use the warm-up procedure to directly compute the policy gradient. Right? Any questions so far? Okay, great. Okay, so let's do SGD. All right, so let's see, for now, forget about reinforcement learning, right? Let's just try to optimize this objective function, j theta, which maps from a vector theta in d-dimension space to a real number, right? Maybe this j theta can be written as a regression loss function, right? So I'm trying to regress from x to y, and my function is a square loss, right? Maybe that's my function. So stochastic gradient descent minimize this objective function as follows. So you start from some initial guess. So you fix some theta 0, and then you just repeat the following process by following the stochastic gradient. So this is so what do I mean by stochastic gradient? It basically says that the expectation of the gradient happens to be the gradient of this objective function at the current solution theta t. Right? So in other words, my GT is an unbiased estimate of the gradient measured at theta t. All right, so let's take a look at this example. So what's a candidate for an unbiased stochastic gradient? Right, so what I can do is I just sample a pair of x, y based on this distribution that defines the expectation, right? Sample x, y and compute the gradient with respect to theta of the loss function measured at this particular example pair, right? And by chain rule, this is just 2 times f theta x minus y times the gradient theta. Right, so this is my stochastic gradient, right? Because my xy is sampled based on the distribution that defines the expectation, right? And of course, you can do mini batch. Sample xi, yi, or I equal to 1 to n in the way of I in an ID fashion, right? And then your gradient is just 1 over n, sum over I equal to 1 to n. Right? I just sample n data points, I compute the gradient for every pair, I sum them together, take the average. Right? So we should hope, this approach to the gradient j theta as an approach to infinite, right? Just by, law of large number. Right, so that's the common approach you're going to use for optimizing a neural network. For instance, here, if you can think about this f theta as a neural network, where theta is the parameters of the neural network, that's the approach you're going to use for optimize, for training a neural network for a regression task. Right, so you either do gradient descent on one particular pair of example, or most likely you're going to do gradient descent using a batch of examples. So here n in practice often is 32, 64, 100. 28 or something, right? So this is a parameter that you're going to tune in practice. Right, so that's the algorithm of stochastic gradient descent, one of the most popular algorithm people use to optimize today's large neural network. Right, as you can see, this is very simple, and computing the gradient is not super computation heavy, right? And you can do all these kind of things using GPUs and using these order differentiation tools that people developed, like TensorFlow or PyTorch, right? I wish we have time to talk about backpropagation for neural network, but I don't think we have time to cover that in this class. Backpropagation is one of the most fundamental idea, like one of the most fundamental algorithm, right? It's more than chain rule. It's an algorithm that actually efficiently computes the gradient for this neural network structure. Right. So anyway, so all I was saying is that, we're not going to really worry about how to compute this gradient efficiently. Let's just assume, if I give you a point x, we can compute this gradient. Right. So we are not going to dive into how we compute this gradient. If we had time, I would like to talk about backpropagation for neural nets. At least, recall what that is. I'm sure some of you probably have seen it before. Right? Okay, so here's this picture, right? So if I run gradient descent, in this example, it's just this straight line, right? But if I do stochastic gradient descent, I'm taking detour maybe, but in expectation, I'm sort of still converged to the optimal solution, right? So the unbiasedness says that, some point I'm biased towards this direction, but sometime I just bias towards the other direction, right? So the bias to different direction is equally likely. So hopefully in average, these things cancel out. In expectation, I still converge to the optimal solution. Okay, any questions so far for this algorithm? Okay, great. So let's just talk about like under what conditions this algorithm will actually converge to a stationary point, right? Okay, let's just directly consider a non-convex objective function. All right, let's be ambitious and let's try to see if we can optimize a non-convex optimization, a non-convex objective. Right, so we need some assumptions on the function. All right, so these two equations looks complicated, but let's just first stare at the first equation, first inequality. This basically says that the gradient of this function behaves smoothly, in the sense that if I change the two inputs a little bit, the change in the two corresponding gradients are not so big. It's bounded by the change of the two inputs times a constant beta. Right? So in other words, if your function is second differential, like twice differentiable, this basically says that your Hessian or your second derivative is bounded. Right? Because this says that the gradient does not change too fast. There's no dramatic change in the gradient if you change the inputs. Right? Your second derivative is well behaved. Like your function does not have a point where the second derivative is infinite. Right? So think about a function, this quadratic function, for instance. Oh, sorry. So think about this quadratic function, right? So the second derivative is 1. So this is a beta. This is a beta smooth function. This is x squared, second derivative equal to 2, I guess. All right, so the second inequality is equivalent to the first one. So we're not going to prove that, but this is equivalent, right? Essentially saying that your second derivative is well behaved, right? Because this is the first order approximation of your function at theta 0, and this is a function, right? So what's inside this absolute value is roughly the second order information, right? If you think about you do second order Taylor expansion of J, then you take the difference of your function value and the first order approximation. What left is roughly the second order approximation, right? So this is the second order approximation. The Hessian is well behaved. Right. So if that's the case, then we can really show that SGD succeeds in the sense that it finds a local minimum solution in expectation. Right. So if we run SGD, so if we run this algorithm for many, many iterations, and if our estimation is unbiased, right? So this condition says that it's an unbiased estimate of my gradient. The second one says that the expected square norm of my gradient is bounded, in the sense that my gradient does not blow up. Right? My function's gradient is always bounded. So the second moment. Okay, so if that is the case, then this says that in expectation, the average norm of my gradients along the waypoints that I computed is shrinking to 0 in the rate of 1 over square root of n. Square root of t, where t is the number of iterations. Right? So this says that if I look at the points that I computed, if I check the gradient norm along these points, so in average, the norm of the gradients is shrinking to 0 in the rate of 1 over square root of t, where t is the total number of iterations so far. Right? So if I run this algorithm long enough, eventually all my points will have tiny, tiny gradient norm. Right? So a local minimum solution is defined as a point where my gradient is 0, actually, right? So think about optimizing a function that looks like that, right? So at this point, so maybe I have let me this way. So I may converge to this point. So this point, the gradient is actually 0, right? This is the global optimal solution, but this theorem is saying that we cannot really guarantee that we will converge to the global optimal solution, but we will at least converge to a point where the gradient is 0, right? Meaning that you're at a place where you look around, there's no immediate way to improve your objective function anymore. Right, so that's the best we can hope for non-convex optimization. Right, so any questions about the SGD for now? Okay, great. So actually, I was planning to go through some of the key steps for SGD, but I think I will skip it for now. If we have time, we will come back and revisit it, right? Okay, so just a quick summary so far. So we talked about stochastic gradient descent for general non-convex optimization. Right? It's a very simple algorithm that can find a local optimal solution in the sense that you find a solution where the norm of the gradient is small, right? In expectation. So the reason that we're talking everything in expectation because this is a randomized algorithm, right? Every round you're taking a random gradient. It's just the gradient is an unbiased estimate of the true gradient. Right? And for convex function, this guarantees global optimality, right? So convex function, think about this kind of square function, right? So a point that has gradient equal to 0 is a global optimal solution. Right? So that's the first part of today's lecture. Okay, so now I want to stop here for a second, see if you have any questions for gradient descent. Okay, great. Okay, so now let's go to the second point, where we will see how we can actually compute gradient using this trick called importance weighting. All right. Okay, so let's say I want to optimize this function, j theta, but my j theta is parameterized in this way. So instead of parameterizing some function, I'm actually parameterizing the distribution where I sample x. Right, so maybe think about p theta as a distribution where you parameterize the mean by theta vector, and maybe the covariance is fixed. Right, theta in Rd. And f is a fixed function that maps from Rd to a scalar, maybe. Right? So this is slightly different from the usual optimization objective function you will see. Here, I'm parameterizing a distribution. Right? So I'm trying to find a distribution such that the expected value of f is maximized or is minimized. I'm trying to find the best distribution, such that the expectation of the function value f is optimized. Right? But in high level or in the abstract level, this is still a function whose parameter is theta, right? And the output is a scalar. So I can still compute the gradient of this objective function with respect to my parameter theta. Right? But this is a little bit complicated to compute, right? Because if you write this out, this is like integral over theta of p theta x of fx. Sorry, what I'm doing here. Okay, so integrate over x dx. Right, so we can push the gradient. So if you do gradient update, we can push the gradient inside the integral. Right, we can compute the inner one, but then we have to take an integral over all x. Right, so that might not be doable. even if your P theta is a Gaussian distribution, for instance. Because we know how to do integral for Gaussian distribution, but once you take a gradient with respect to the distribution's parameter, who knows what that form is, right? We might not be able to evaluate the integral at all. So we were trying to figure out a way where we can approximate this gradient using samples, right? In other words, we were trying to figure out a way where we can get an unbiased estimate of this gradient without doing any sort of complicated integral. Right? So I'm just rewriting the expression. Okay, so now let's try to make our life easier. So suppose that I have a sampling distribution rho. So rho is a distribution for x. All right, and this rho is pretty nice in a sense that this covers the current distribution P theta. Right, so here you should just think about this as, maybe this is my rho and this is my P theta, right? So my rho has wider coverage than my current distribution P theta, right? So the reason that I assume that because I want to make sure, I don't put 0 in the denominator, right? Because that's gonna make things undefined, ill-defined. All right, so we have this nice sampling distribution. Now I can actually do this trick, right? So this is exactly the importance weighting trick. So I can rewrite this objective function as expectation of x from rho and then rho x over P theta x, right? So this, by definition, is equal to integral of rho x times rho x P theta x, which is integral over x of P theta x, which is expectation of x over P theta, right? I just multiply rho x and immediately divide rho x. Right, so you can think about this two cancels out. Okay, so I do this importance weighting. So now I get expectation with respect to my sampling distribution rho, right? Instead of my distribution P theta, which is going to be optimized. Right, now I can just push the gradient inside the expectation because the expectation has nothing to do with my parameter theta. This is a fixed sampling distribution for now. Right, so think about rho as a uniform distribution for now. This works for uniform distribution, right? So I just push the gradient inside the expectation, and this is the only term. This is the only term in these three terms, right, where I need to compute the gradient because this is the only term that depends on theta. All right, so why this is nice? Now we can actually draw samples from rho and we can approximate this gradient using average. So let us sample x1, xi, I equal to 1 to n, iid from rho. Right, I just sample n points from uniform distribution. I plug into this formulation. Right, I get an unbiased estimate of my gradient actually. Right, so that's pretty nice, right? In the sense that now I just use a uniform distribution and I do this, importance weighting trick. I multiply rho x, I immediately divide rho x. And now I can actually write the expectation using my sampling distribution rho, right? And now I can just sample points from rho and averaging them together and get an unbiased estimate of the gradient, the original gradient, right? So this is an unbiased estimate. All right, so with that, you can use, gradient descent or gradient ascent to optimize this objective function.
Professor, I have a question. So previously you said that P of theta might be like a normal Gaussian distribution, and then we know the variance, we don't know the mean vector, and then you said if we are going to take derivative, then that's going to be very hard. But here we're like the term on the numerator is still like taking derivative of a parameterized distribution, right?
Yes, but it's just on one point, right? I'm not going to do integral. So here, if you just directly do this, you're going to do integral over x and the gradient theta of p theta, integral is it time fx, right? So you're going to evaluate this for every x, and then you're going to do integral. So here, when I compute this, I'm just computing gradient at the points where I sampled.
Okay.
Right? I don't want to do, I really don't want to do this integral, right? Like it's.
Okay. So the hard part for the previous approach was the integral was hard. The derivative was not hard.
Yeah.
Okay.
Yeah, derivative could be easy, right? Like think about implementing this p theta in TensorFlow. You can compute the gradient using backpropagation for any point, right? But you cannot rely on TensorFlow to do integral for you because like for a lot of cases, it just doesn't exist, right? I mean, it exists, but you cannot compute exactly, right?
Thank you.
But like here, in this simple formulation, right? Just sample endpoints, ask TensorFlow or PyTorch to compute gradient for these endpoints in parallel, just average them together, right? You're good to go. Okay, so any questions for this importance weighting trick?
What is rho of x?
Yes, so it's a so think about rho as a distribution, a uniform distribution over space x. Okay, so rho x is just the likelihood of the probability of seeing this point x, or the likelihood of seeing this point at x.
Oh, okay, thank you.
Okay, so one more step left. This is pretty much the final step, but there's one more step left. We want to simplify things. So imagine that at some point we are at theta 0, right? And we're just interested in computing the gradient at the point theta 0, right? So this expression is saying that I compute the gradient and evaluate at my current point theta 0. Right, so this is like gradient descent, right? Like I'm not interested in computing gradient everywhere. All I'm interested in computing the gradient on the position where I am right now, so that I can take a gradient descent or gradient ascent. Right, so imagine that we are at theta 0, and we're just interested in computing the gradient at theta 0. All right, so if you recall this importance weighting trick, we can replace rho by any distribution, as long as this property holds, right? So now we can just replace rho by our current parameterized distribution, right? So this is available because we are currently at theta 0, right? Imagine, you start gradient descent by initially guess theta 0, and now you want to compute the gradient at theta 0. So rho p theta 0 is given, right? Because this is the parameter that we have in our hand at this moment. So I can just set rho equals to p theta 0. And if I plug in this into the above expression, I get into this very nice log likelihood expression. Right? So this might look a bit weird at first place, but just think about chain rho. Right? What's the gradient of the log?
One over f.
And right, so let's
That's
just
the gradient of f.
Yeah. Right, so that's just chain rho for this composition of log and a function f, right? So now let's look at what happens if we do this in multi-dimension, right? So this is essentially just equals to p theta 0 x gradient theta p theta 0 x, just by chain rule, right? I first take derivative with respect to log, which gives me this 1 over p theta. And then I take gradient with respect to the term inside the log, right? And this is exactly matched to what we have, right? By setting rho equals to p theta 0.
So this is essentially the reinforced trick in disguise, right? The log
Yeah.
derivative.
Yeah. So yeah, so we are doing this. Yeah, so we will see this trick actually just immediately applies to reinforcement learning. So here I'm just doing this for, a regular sort of like non-Markovian decision process setting. Right? But you will see immediately, yeah, that
It
just
would be valuable to elaborate on why the gradient of the log is easy to estimate using Monte Carlo estimation, while you can't estimate the original.
Yeah.
Monte Carlo.
Yeah.
You
Yeah.
can't,
Yes, good point. Yeah. So yeah. So before we talk about the point that Hadi was mentioning, I just want to see if we have any questions for now. Right. So this is the first time that we see this importance weighting trick in this class, at least. Right. So I want to make sure everyone feels comfortable about this distribution change trick. It's not really like a trick, right? This importance weighting is being used over and over, like in many aspects of machine learning, actually. Okay, so now let's talk about the sampling procedure, right? So again, this is nice because my expectation is with respect to my current distribution, right? So I can just sample points in my current distribution. Sample x from p theta 0 and compute gradient theta log p theta 0 at the sampled point x, right? I don't do any integral evaluation times the value of the sampled point. That is my unbiased estimate of the gradient, right? Just by the definition of expectation, right? Then I do gradient descent or gradient ascent based on whether whether or not you're optimizing or maximizing or minimizing the objective function. But you just do a gradient update. Now you get to theta 1, and let's repeat the same process. Right, so this is the stochastic gradient algorithm for optimizing this type of objective function, right? Where this is a little bit unusual, in the sense that we parameterize our distribution, right? So this is like, those recently, like those generative adversarial net GANs, so the GAN problem, right? You parameterize the distribution, and the distribution is trying to generate maybe, realistic image, right? So you have to do gradient descent on the parameters of the generator, the image generator, right? So think about image generator as a distribution, right? So you're trying to parameterize the generator so that the image sampled from the generator looks like real image, right? So maybe your function f is measuring the realistic of a sampled image, right? So that this kind of parameterization is also common nowadays, in machine learning. All right, so let's just look at this particular example, right? So, so here, imagine that I'm trying to maximize. I'm trying to do maximization. Right, so this is my function. So my function looks like this, right? And instead of controlling the function, I'm controlling the distribution here. So imagine my distribution is just a Gaussian distribution, is a normal distribution. In this case, it's just theta 0, sigma squared, right? I'm just trying to control the mean of my distribution, right? So that when I'm evaluating the expected value of my function f, I maximize that value. So in other words, ideally, I want to push this distribution to left so that the peaks of the f and the peaks of the distribution, they sort of, they align with each other. Right? So in other words, if I do one step of gradient ascent, intuitively, I basically push the distribution a little bit left. right? Because now, the peak of the distribution and the peak of the function, they are slightly more aligned compared to the previous distribution, right? So when I do gradient descent, I'm gradually gradient ascent. I'm gradually pushing the mean of my distribution a little bit left, right? So in other words, I really want to parameterize distribution such that it puts a lot of probability on the points where the value f is high, right? So I want to put a lot of probability on these points, right? I want to put tiny probability on these small value points, right? So that's exactly what this green curve is trying to do. Right? So in other words, we update the distribution by indirectly updating the parameterization of the distribution, such that p theta has high probability mass at regions where fx has high values. Right. So intuitively in this picture, think about you're gradually pushing this distribution, this radial curve, to the left. Eventually you reach to the green curve, right? Which might be the optimal solution for this parameterization. Right. And as I drew it here, this function could be arbitrary function. Like it doesn't even need to be convex. Right. So this same philosophy holds for any function f. This could even be a non-differentiable function for f. Because remember, our expression does not take derivative with respect to f at all, right? This is just a fixed function. So this could be non-convex, it could be non-smooth, it could even be discontinued, right? Right, so we will use the same idea for reinforcement learning. All right, so that's the end of the warm-up, and I want to stop here for a second, see if you have any questions. So I think this is a very important point to understand before we jump into reinforcement learning. Right, so I want to emphasize, this expression is particularly nice, right? We only take derivative with respect to the log likelihood of our distribution, and we never take derivative with respect to this function f. So this function could be any function, non-convex, non-smooth, right? As long as we can evaluate this function's value. Because if you recall the unbiased estimate is just the average over these points sampled from this distribution p theta 0, right? Right. All I need is a tool that can compute the gradient with respect to this parameterization p theta at a given state, at a given point xi, and another black box that returns me the value of this function. I don't even need to know the form of this function f, right? As long as I give you an x and you give me a value, then I can already use that to compute the unbiased estimate of the gradient. Right? We never needed to know, the form of the function f. This could be some black box complicated function. Right, and oh, sorry, I forget the gradient form. All right, so let's actually just go to policy gradient. Right, so before we jump into policy gradient, let's see, what kind of common parameterization that we will use for parameterized policies. Right, so the simplest parameterization is this softmax parameterization for discrete or tabular Markov decision process. Right, so for each state action pair, I'm just going to design a parameter, a scalar, And I'm just going to design my policy, the stochastic policy, as this softmax. Right? So P theta, this is a valid distribution. Right? In other words, sum over A, pi theta AS equal to 1, and pi theta AS is bigger than 0 for A. Right? So this formulation gives us a distribution. And another parameterization is basically, the logistic regression, right? So think about A is a class. So you have finite number of actions, you have finite number of classes. So specifically think about the case where you only have 2 actions. So you're doing binary classification. And let's just assume that we have a feature vector phi, right, that maps from state action pair to a real vector. Right? So in LQR, it's just concatenation. Maybe it's just the concatenation of the state and an action. And let's just design a parameter, a linear function parameter theta, and then let's just do the softmax again. Right? So this is literally the logistic regression formulation for binary class classification. Imagine you only have 2 actions, A and A prime. Right? Again, this is a distribution over the action space. Right? So the last formulation is that we can use neural network, for instance. Let's just design a neural network as a function that maps from state action as input and outputs a scalar. Right? So maybe this guy is approximating Q star, who knows, right? Or maybe it's approximating some C Q star times, a constant, right? Intuitively. And let's just add this softmax on this F's value. Right, so if in this case, sum of F theta star equals to a constant C times Q star SA, then this expression really is saying that I should design a policy such that it gives very high probability of sampling an action whose Q value is big, right? Because this is exponential. So I think the bottom line is that, in high level, we should really think about pi theta as a classifier, right? And it has its own parameters to be optimized. So it's really a classifier that takes, the state as the input and tells us a distribution over these classes where each class is a label. Sorry, each class is an action, right? So it's literally a classifier. Like we can parameterize our policy using any, differentiable function approximation, logistic regression, and neural nets, for instance, right? So this is literally the expression of a neural net for classification problem, right? So you have maybe multiple layers, and at the end, you apply this to softmax layer, and then outputs a distribution, right? So this is input S, and the output is a distribution over actions, right? Over labels. Right, so policy gradient is really powerful because it allows us this flexibility to design policy parameterization, right? And all we need, as you will see, is that the ability to compute the gradient of log of pi theta. That we can do by just implementing this neural nets in TensorFlow and take a log on top of it and ask TensorFlow to do a back propagation. Right, so that gives us the gradient, gradient of the log likelihood. And for softmax, for this parameterization, you can just calculate the gradient by hand, right? And this is actually what we will try out in the next homework. Yes.
Can I ask a question?
Yep.
Let's just look at the neural policy, right?
Mm-hmm.
Is there a relation between f theta SA and the Q function? It seems like they're proportional.
Yeah, so one way to think about this is that, maybe you're trying to find a theta such that f theta approximates, q star,
Mm.
right? Because this softmax parameterization is really saying that if you have a class that has high value, you should give it high probability, right? You should like increase the probability exponentially,
Mhm.
right? So this is this policy parameterization C, right?
I see.
So imagine in the limit, you have two actions, right? At the particular state, one action has huge value, one action has tiny value. So this distribution parameterization is literally going to output an almost deterministic distribution, right?
Yes.
Because you do EXP, because you exponentially, increase the probability, right?
Got it. Thank you.
Yeah, but this is literally classified, right? This is just, this one is logistic, linear logistic regression. This one is linear logistic classification. And this one is just neural nets classification, right? And for multi-label classification. I mean, if you're not comfortable with multi-label, just think about example where you only have two actions, right? We are okay for now for dealing with the MDP where we have two actions, but we have potentially infinite many states. And maybe think about playing simple video games. You only have two actions to control for the agent, but the state is in an image, right? It's a raw pixel image. So you have huge amount of states, but you have two actions to control, right? Every time you just needed to do two-way classification. So that's all this slide is saying. All right, so with that set up, let's talk about policy gradient. Okay, so let's record the definition of a trajectory. So this is a sequence of state action pair starting from time step h equal to 0 and all the way to, it's an infinite length trajectory, right? Because we're in the infinite horizon discounted setting. But we can actually literally using the Markovian property to write out the likelihood of this trajectory, right? Which is just the product of a bunch of this transition term times the transition term and the policy gradient, the policy form, right? So this is the likelihood of sampling S0. This is the likelihood of getting A0, conditional S0. This is the likelihood of transit to S1, conditional I've already seen S0, A0, so on and so forth, right? So we can just literally write this out. Okay, so this is nice in a sense that now I parameterize policy pi theta. This gives me a parameterization over the trajectories. I get a distribution over trajectories, right? So for each possible trajectory, I can just evaluate its likelihood by using my policy, right? So like we cannot evaluate it exactly because we don't know P, right? But at least this quantity exists. Right? So pi theta determines this rho theta. All right, so let's just write out the objective function, right? So we can write out the objective function using this trajectory distribution. So I sample a trajectory from this distribution. And inside this expectation it's just a straight sum of the rewards on this trajectory, right? This is by definition is the expected total reward of this policy, right? Because now I have a distribution over trajectory, and I'm just doing integral over this, over all trajectory weighted by the likelihood of sampling that trajectory. And we know the likelihood of sampling a particular trajectory is evaluated using this product of policies and transitions, right? Just by Markovian property. Right? So now let's just abstract the inner expression inside this expectation as a function of tau. Tau is just very simple. It's just a straight sum of the rewards along the trajectory, right? Right. In other words, you give me a trajectory this R tau is a black box that looks at the trajectory and returns the total sum of the rewards with proper discounting. All right, so now what do we get here? So we're really optimizing this function, right? Right, we are optimizing this distribution rho tau such that the expected total reward measured under this function R is maximized. Right, so if you recall the warm-up example, this is what we're doing, right? X from P theta and Fx, right? So here I'm literally doing the same thing. So P theta here is this rho theta, X here is a trajectory, and Fx here is this function R tau that just looks at the total sum of the reward across this trajectory, right? So these two expressions, they're almost identical, except that I replaced, X by tau. But if you abstract tau as a point in infinite dimensional space, they're literally the same, right? And conceptually, I'm just trying to control theta such that I find a distribution rho theta that puts a lot of probability mass on trajectories that has high reward. Right? That's all we're trying to optimize. Okay, let's just go through the rest, 3 or 4 steps, and then we can, pause and sort of trying to explain this more. Okay. All right, so I want to compute the gradient of this guy, of this function, at our current solution theta 0. Let's just use the derivation that we had, right? So remember, gradient theta of this function, expectation of X from P theta. Right, so this is our warm-up example, and we measure that theta equal to theta 0. So we said this, we've convinced ourselves this is equals to the expectation X from P theta 0 log P theta 0 and X times Fx. Right, so in this step, I'm just literally using the derivation that we had from the warm-up step, right? I'm replacing F by this R, and I'm replacing P theta by this rho theta. Right, so this is the same importance weighting trick. Right, so here I haven't used anything about, the form of the rho theta yet. So here I'm literally just using the calculation that we had in the warm-up example, right? Just do the importance weighting and do the chain rule on the log likelihood, right? Okay, so this is an okay expression because we don't really know how to compute this gradient, right? Because we don't know the trajectory likelihood because P is unknown, right? Like it exists, we can define it, but we cannot calculate it. We cannot use TensorFlow to calculate it, for instance, right? Because we don't know how to compute this term because P is unknown, right? So this is not a good sign because like we can literally we can't implement this expression rho theta, right? Because P is unknown. This is unknown, right? We are in the learning setting. We are not in the setting where everything is known. Okay, but we can apply a nice trick here by just writing out the expression of this trajectory likelihood. So let's just do that, right? So if we start from here, what is the log of the trajectory likelihood? Right? Log is nice because log of the product is a sum of log, right? So this is log of mu S0 plus log of pi theta A0 S1 plus log of P S1 S0 A0 plus, right? Okay, so this is great because if now we add this gradient expression on both sides of the expression. Okay, so let's do gradient log rho theta tau. Right, so this is gradient theta log of mu S0 plus gradient theta log of pi theta A0 S0 plus gradient log of PS1 given S0 A0 plus, right? Okay, so now we can see something that is nice gonna happen, right? So this term is 0 because this is a initial distribution that has nothing to do with my parameterization. I parameterize policy, right? And the initial distribution is given when the MDP is given, right? Like we don't get to choose the initial distribution. That's a given quantity, right? We don't parameterize it. We only parameterize our policy. Same thing for this term. Because the transition is given at the moment when this MDP, this game is defined, right? Like we don't get to choose the transition. We only get to parameterize our policy. So this is 0. Right? Because P and mu, they're not depending on theta, our parameterization, right? Okay, so in other words, this is 0, I can just get rid of it. This is 0, I can just get rid of it. The terms that matters are basically this term, right? This makes sense because I'm actually controlling pi. Like we, as the designer, we designed this parameterization, right? So pi is a expression that depends on our parameter theta. And this is not going to be 0. Right? So let's cancel all these terms, 0 terms. And what left is just the summation of this log likelihood of my policy. Right? And let's and let's just rearrange terms, right? So all we have is just a summation of these log terms, log likelihoods, right? Right? And multiplied by the total reward on this particular trajectory. Okay, so why this expression is nice? Because we parameterize policy, right? And evaluating gradient of this log policy at a particular state action pair. This is doable. You just implement this parameterization in TensorFlow, add a log on top of it, and call the backpropagation function. You're done, right? And for logistic regression, we know that we can compute the gradient by hand. Right? Because this is a function that we control, right? We know the like we know everything about this policy because we parameterize it. Like think about, logistic regression, right? We have full control on this distribution, but we don't have control on the log trajectory likelihood because we don't know the transition, right? But the nice thing is that when we take the gradient of this log of the trajectory likelihood, all these terms, they get away, right? Sorry about that. This should be mu0. And this term also goes away because they're not depending on my parameterization theta. Right? So in other words, if you do gradient ascent update for optimizing this function, you're basically trying to control policy such that you're going to put high probability on trajectories that have high rewards. Right? You're trying to control your policy such that you indirectly control the trajectory distribution, such that the trajectory distribution literally have high probability on trajectories that has high value. Right? And when you do gradient update, you're sort of pushing the parameter such that it gradually moves the distribution mass towards those trajectories that have a high value. That's all this procedure, this optimization procedure is trying to do, right? If you recall the 1D case, the 1D example that we showed, right? We're trying to push this distribution all the way to left such that the distribution has large probability mass on those regions where the function value is high. So here I'm indirectly controlling my process by first controlling the policy, right? And then, by adjusting the parameters of the policy, I'm adjusting the trajectory distribution so that gradually it puts more and more probability on a trajectory that has high reward. Right? So it's just, we don't have directly control on this trajectory distribution because we don't know P. But we do have directly control on the policy because we designed this policy, right? All right, so just a quick summary so far. This is the expression that we get, right? And how to get an unbiased estimate. So imagine that we can just sample the tau from rho theta tau, and then just calculate this term. Right? Remember, this is just a straight sum. Right? I'm adjusting, basically I'm adjusting the parameter based on the reward of the trajectory, right? So if the sample trajectory has high reward, then my gradient is actually linearly proportional to that. Like the magnitude of my gradient is actually linearly proportional to that reward, right? If I happen to sample a trajectory that has high reward, then this is great. I should really, leverage this experience to push my gradient as hard as I could, right? So this is this R tau is saying. So if I happen to sample a trajectory that has tiny reward, then I probably should not really move my gradient that much, right? So this is this unbiased estimate is basically saying. Okay, so, and you can do the same exercise. This is literally the same process for finite horizon Markov decision process, which is actually a very common setting in policy gradient formulation, right? So all I'm doing is just replace the infinite by this capital H minus 1, because we only have capital H minus 1. We only have total capital H steps, right? The rest is the same, except now the R tau is a straight sum of the rewards across this total H minus steps. Right? The rest is basically the same. Same trick of importance weighting and same trick of applying this log on the trajectory likelihood, and then on top of it, apply the gradient formulation. Right? So this is even nicer, right? So I can just sample a tau from rho theta tau, and I can just form the gradient formulation. Right? And you can sample multiple trajectories if you want and take the average, right? So this corresponds to a mini batch stochastic update. Okay, so the last thing that I yeah.
Sorry.
Okay, but yeah.
For the previous infinite horizon setting, how do you actually sample like an infinite trajectory?
Yeah, so that's a good point. You will not exactly be able to do that. And what you can do is truncate at a particular time step. Right. So imagine you sample really long trajectory, right? And let's see you stop, at 200 or 300 and your gamma factor is 0.999. So afterward, after 200 steps, the contribution will be tiny, right? So you get a slightly biased gradient estimation. Okay, so that's why I said like this finite horizon setting is actually more common in practice, right?
Another question that I have for finite horizon setting.
Yeah.
So if I understand this correctly, so essentially what I need to do is for every gradient, for every update, I have to restart the game multiple times to get different trajectory.
Correct.
Calculate this value, average them to get a gradient estimate, and then perform gradient descent or ascent.
Yeah, correct. Yeah.
Okay. Got it. Thank you.
Okay, so the last thing that I want to quickly mention is that you can simplify this formulation by just writing this function r tau. Wait, what? Oh, not like here. Sorry about that. You can actually write this formulation by just looking at the summation of the reward starting from time step h. Okay, so actually, I'm gonna skip this. We're gonna revisit this in the next lecture, right? Okay, so let's just quickly summarize what we talked about. So we talked about this importance weighting trick, right? So that allows us to do sample and then evaluate the gradient, right? Get an unbiased estimate of the gradient. And then we talk about policy gradient. This algorithm is called reinforce. This is a direct application of our warm-up example, right? And this is the formulation that we get. We try to push the trajectory distribution based on the reward of trajectory, right? So the goal is to find a policy such that it assigns very high probability on the trajectory that has high reward. And a byproduct is that we can use unbiased estimate of any function, the gradient of any function, and then do stochastic gradient update, and that will actually converge to a local optimal solution. Right? So this also applies to reinforcement learning. So once we get this formulation, and once we can get some GT, where the expectation of GT is the gradient of J theta t, then we can just deduce theta t plus 1 equals to theta t plus eta times GT. Right? So this is just a straight stochastic gradient ascent that should converge to a local optimal solution.